Welcome to topic 8.1. This is where we're going to introduce how we start counting atoms, molecules, and formula units. So these are working through conversions. It's been a little while since we've done the math, so you're going to see a few topics come back that we reviewed first semester and worked through. You will want your periodic table, calculator, and polyatomic list to work through this. So again, this is our introduction. By no means are we done with mole conversions after this. And when we do our lab, a lot of this will start making more sense once you have things in front of you. So to start, we're going to start with, again, quantifying material, and we do that through a unit called the mole. It's abbreviated MOL. Yeah, I know it saves you a lot of handwriting, but it's a way for a chemist to count particles. And so what we have developed is what's called Avogadro's number, and it represents how many particles you have within a mole of a material. And so if you have a mole of a substance, you have 6.022 times 10 to the 23rd of these representative particles. So here, this is sulfur, iron, sodium chloride, potassium dichromate, sucrose, aka table sugar. If you take a look, and I know it's in black and white, but you can obviously see there's different quantities of each chemical in these beakers. And so what they all have in common is that this is all 1 mole of a substance. They all have 6.022 times 10 to the 23rd atoms, molecules, or formula units, depending on what kind of bond is holding them together. So representative particles, again, this is all based on what the material is held together with. So if you take a look at something and it's found on the periodic table, meaning it's an element, we typically count them. Their representative particle is the atom because they're not bonded with anything. They exist on their own with no interaction with the other atoms that are surrounding it that have the same identity. So for example, iron and helium are both examples of things that are atoms. However, there are some elements on the periodic table that are not considered elements, and those are considered molecules. And those 7 are the diatomics, those Hoffen-Kleiber molecules. And so hydrogen is one of them. So hydrogen doesn't exist on its own as a single hydrogen atom, but more or less as a hydrogen bonded to another. Same with the remaining 6 Hoffen-Kleibers or diatomics, it's bonded with itself. So its representative particle is the molecule. Other things that are also referred to as a molecule include water and sulfur dioxide. They are all held together with covalent bonds. They are all non-metals. So the other type of compound that we discussed earlier this year are things that are ionic. And so we count them in a particle called a formula unit. So we have calcium chloride, iron 3 oxide. Those are, again, all counted as formula units because they are held together through an ionic bond. So we're going to kind of just dive right in and start working on some conversions. So when we first started conversions, the very first thing we would do is we would identify our given. So when we read through the problem, a given has 2 parts. It has a quantity and a unit. And so we can see quite obviously the problem tells us we have 4 moles. Moles is abbreviated MOL. And then the other thing you're going to want to get in the habit of is start including what it is. So this isn't just moles, but this is specifically moles of iron. The problem is asking us to solve for how many atoms. So Avogadro's constant is 1 mole is always equal to 6.022 times 10 to the 23rd. The unit can vary between atoms, molecules, or formula units depending on the material you're describing. So when you set up a conversion, that means the denominator needs to be 1 mole. It is equal to Avogadro's constant of 6.022 times 10 to the 23rd. And this is atoms. So a couple of things. When we set this up, the unit you have is the unit that goes below. We can show that those have canceled. Mathematically, what you're doing here is multiplication. The other thing is we have to keep track of sig figs. This is Pacific, so this has 3 sig figs in the given. Therefore, we can keep 3 sig figs in our final answer. If you need help putting this into your calculator in scientific notation, please speak up and let me know. But I'm going to multiply this, and when I do so, I get an answer of 2.41 times 10 to the 24th atoms of Fe. and then we are done. Okay. In the next problem, we're working with the same constant because we are counting one of our representative particles. So in problem 2, we're given 3.01 times 10 to the 24th. Molecules, we do have an abbreviation, MCule, and carbon dioxide, so I'm going to include the what it is as CO2. It wants to know how many moles there are. So like the last problem, we were solving for moles. And so to do so, we take Avogadro's constant, 6.022, times 10 to the 23rd. And we're going to put that in the denominator. We need to divide to make them cancel. Therefore, my numerator is 1 mole. So mathematically, again, in this problem, you should divide. When you run that through on your calculator, when you do sig figs, this part does not influence sig figs, only the 3.01. It has 3. So when I type this in with 3 sig figs, I get an answer of 5.00 because originally you get like 4.998 and it does some rounding. So this is 5 moles of CO2. Again, by adding those 2 zeros after the decimal gives me 2 more sig figs. In example 3, we're looking for formula units. This is the last remaining representative particle because again, this one's held together with ionic bonding. It tells me it's magnesium hydroxide, so I know magnesium is Mg. Periodic table tells me it's a +2. Hydroxide, according to the polyatomic list, is OH. It's a -1. So the formula of the compound we're working with is MgOH2. So my given is 1.20 moles of it. Again, I'm going to include the what. Because my given is in moles, I must divide by 1 mole, and that puts Avogadro's constant in the top. So this has a very classy abbreviation, so formula units. And then from here, we're going to multiply. When I look at my given, this has 3 sig figs, so my answer can keep 3 sig figs. Again, scientific notation doesn't count towards it, so when I get to my answer and with rounding, I get 7.23 times 10 to the 23rd, and this is formula units of magnesium hydroxide. And that is how you work with Avogadro's constant. Now, the other part of this lesson is working with a calculation called molar mass. So in a chemistry lab, we don't have scales that count atoms, molecules, formula units, or even a scale that counts moles. The only thing a scale is allowed to measure and is able to measure is mass in grams. So traditionally, more of our conversions involve the use of molar mass, and it's a quantity in grams of that atomic mass for that element. It has a unit of grams per mole, or we abbreviate it as G/mol. This slash is read as per, which means divide. So how many grams you have in 1 mole. Your periodic table tells you the molar mass of any element. So for calcium, for example, here it's 40.078. So we're going to cut that off to 2 decimal places. So the molar mass for calcium, I would use 40.08 grams per mole. Okay. Lead, I find lead here. It's 207.2, so its molar mass is 207.2 grams per mole. And then the last one, neon. Neon is right here. It would be rounded as 20.18 grams per mole. All right, so that's how you find molar mass of an element. Now we're going to look at how to find molar mass of a compound, and I'm only going to work out 1 and 3. So the first thing is kind of similar to balancing. The first thing I do is I list out the elements I have. So I can see table salt or sodium chloride is made out of 2 elements, sodium and chlorine. The next thing I need to know is how many I have of each. Because there's no subscripts, I have 1 and 1. Sodium, when I go to the periodic table, just like I did in my previous problems, it's 22.99. Chlorine, it's 35.45. So essentially, we're just adding the mass of chlorine to the mass of sodium, and we get 58.44 grams per mole. So then for number 3, when you go to take an inventory, you have 3 elements. There is aluminum, sulfur, and there is oxygen. When you take a look, we have 2 aluminum. Through distribution, we multiply, we have 3 sulfur and 12 oxygen. Again, we then go to our periodic table to find their individual masses. So aluminum is 26.98 to 2 decimal places. Sulfur, we can round to 32.07. And oxygen bumps up to 16 flat. Again, what you're doing is you would multiply and then add these all up. And we get an answer of 342.17 grams per mole. That's going to help us with the other style of conversion. So here, if we need anything that starts with grams or ends with grams, we need molar mass. This problem gives us 0.75 moles of silver. It's important to ask myself, is silver Hofenkleiber? It is not, so it's just Ag. And it wants to know grams. So that means I need mass. And more specifically, I need molar mass. So because I'm working with silver and it's not Hofenkleiber, this rounds off to 107.87. So the molar mass of Ag is 107.87 grams per mole. That part is important because it helps me decide how to set this up. I set up my conversion. My given unit is moles. This line means per. This line means per. Same thing as division. So I'm separating these into 2 parts. I have the mole part and I have the mass part. The mole is going to become my denominator to cancel. My 107.87 grams is my numerator. So mathematically, I just need to multiply. Tricky one here, that 0 in the front doesn't count. It's only the 7, 5, and 0 that count, so 3 sig figs. So multiplying to get my answer, I get to 3 sig figs, 80.9, and that's grams of Ag. Example 2 is where I'm going to end. So in example 2, we have a box of table salt, and it tells us we have 737 grams of this salt. So I can start by putting 737 grams, and because it says table salt, I know that's NaCl. It wants to know how many moles there are. So in order to go from grams to moles, and just like the last problem, moles to grams, you always need a molar mass. So we need the molar mass of NaCl. Well, we're going to work smarter, not harder. If you look at part E of your notes, the very first one that we set up is for salt. So we're going to just steal that information. So we have 58.44 grams per mole. Again, that was just calculated right above in number 1 of part E. Like the last problem, molar mass helps give me my conversion factor. Because I'm starting with grams, this is the first piece I will plug in or substitute, and I'm going to do that through division to make those grams cancel. That means 1 mole becomes my numerator, and division is what's necessary to solve. Grams is going to go ahead and cancel. This has 3 sig figs, so I'm going to keep 3 sig figs in my answer. All I need to do is work through division. I get an answer of 12.6, and that is moles of table salt. So if you have questions, need help, please come see me or reach out so you can get through these one-step conversions.